Welcome back. My name is Renee Clary, and in this video segment we will discuss mass wasting, or the downhill movement of Earth material by gravity. Mass wasting is responsible for many changes in the Earth's surface, and it also can result in tragic losses of human lives and property. Let's get started. Again, mass wasting is the downslope transfer of Earth material primarily by gravity. After weathering will break apart rocks, mass wasting is the process responsible for transferring the debris downslope to the stream bed. Direct erosion from the stream only carves out a very small part of the rocks. Mass wasting is the process that is going to remove the rest of the rocks. So, if we look at a diagram, weathering and erosion through mass wasting then will bring these materials down to the stream. Through current transport, the sediments are deposited finally out to the sea. And again, the river is only responsible for moving just a little bit of material. In a slot canyon, in the upper diagram, you see the river channel eroding straight down. This is the component for which the river is responsible. However, material on either side of that channel will become unstable and move downslope because of gravity, widening the channel into that nice V shape you see. So the bottom diagram shows us the component that is removed by downcutting of the river, that's in the center, and then the larger components on either side of the main channel are removed by mass wasting and sheet erosion. What would the channel look like if mass wasting were not at work? Here is a slot canyon, for example. The river will remove the rocks directly below its bed, so therefore we end up with this nice canyon that's carved straight down. This can result when the rocks are very resistant. The land is rising fairly rapidly. Mass wasting is affected by many different factors. For example, the type of rock that is involved. Shear strength refers to the material's cohesion, its internal friction, and its external support. This is what's keeping the rock together. The geology of the rock will also affect whether or not it's more susceptible to mass wasting. For example, the dip of the strata, in which direction the beds dip compared to the overall topography on the surface. The strength of the rocks themselves, the strength of the strata, and any fractures that may exist within the rocks. Gravity versus shear strength? Well, gravity usually wins out. Shear strength is what keeps the rocks together. So we have compression, internal friction, and any support keep the rocks and sediment in place. Now gravity, of course, that force moving straight toward the center of the earth, is working against the shear strength. The component of gravity that's acting parallel to that slope that's going to move the material in this direction, if overcoming the shear strength, will slowly or sometimes rapidly move those earth materials downslope. The type of rock and the geology are big factors. So the dip of the beds can actually hasten mass wasting. The top diagram shows permeable sandstone underlain by an impermeable shale. So this can be a recipe for disaster because the beds are going to dip in the same direction as the slope of the hill. So if water infiltrates through, it percolates through and hits that impermeable shale, it's trapped and we can end up with a very slippery surface. And again, note that the beds are dipping in the same direction as the slope. The lower diagram, on the other hand, we have beds dipping at a different angle, so although water infiltrates within, it is not forming a slippery barrier between an impermeable rock layer. The top diagram more likely to see mass wasting than the bottom diagram. The Gros Ventre slide in Wyoming had a similar geology to that top diagram in the previous slide. What happened in Gros Ventre was that the water percolated through a permeable sandstone but was trapped against an impermeable shale. So an entire section of sandstone broke free and slid down the slope, and it dammed the river below. In addition to the type of rock, the slope angle has a big effect on whether or not mass wasting will occur. In this diagram, we can see that the river at the base of the slope can erode away, and if the stream undercuts the slope, we end up with mass wasting. We've removed the support from the bottom. Now, streams aren't the only agent responsible for cutting a slope. In this diagram, you can see that we had a nice slope. A highway was put in, and actually we oversteepened that slope. So this is man-made oversteepening of a slope angle. In this case, it was the hillside that was excavated to make room for the Pan American Highway, and it resulted in a rock fall that blocked the highway. That must have been a mess to clean up. Weathering and climate and the amount of precipitation go hand in hand in facilitating mass wasting. This is along Conchita, California. Heavy winter rains caused the landslide in 1995. 9 homes were destroyed in this landslide. The area is prone to these events. A landslide more recently killed, I think, 3 people. Very famous mass wasting event. This is Aberfan in South Wales. And what you see, that sort of black sludge, is actually a mass wasting event involving the debris from coal mines. The coal that is removed is put in what are called tips. So the coal mine tip was at an unstable position. It was very, very steep, and when rain events occurred, the coal mine tip was very saturated and collapsed and liquefied. It flowed like a liquid. It moved straight down through the middle of the town as a big sludge, and the village school was completely destroyed. All 116 children suffocated. Very tragic event. The good item that came out of this tragedy was that the UK established a coal mine safety commission that specifically investigates these coal mine tips. Mass wasting is also affected by vegetation. Here we see Hamlin in Madagascar. A lot of erosion taking place. Vegetation will anchor the sediments and the soil. When trees are removed, deforestation, erosion can take place. Mass wasting can occur much more readily. Human activities. Overloading of a slope. We add buildings that are very, very heavy, swimming pools, highway substructures. All of this can facilitate mass wasting. Here's an old diagram showing a hillside that's been terraced. We have a home up on one of the upper terraces, but it has a septic tank, so we have infiltration from that septic tank, which is weakening that slope. If we have a swimming pool that's excavated, any leakage from the swimming pool will add water to the soil, again, can cause problems. Triggering mechanisms are also important factors in mass wasting. For example, earthquakes, volcanic eruptions, a lot of rainfall, precipitation events can trigger mass wasting events. And one example of this is Yungay in Peru. In 1970, the glaciers, rocks, and ice high up in the mountains were shaken loose during an earthquake, and the debris traveled very rapidly, over 200 miles per hour. It took only 4 minutes to completely bury the town. 17,000 people lost their lives. And when the geologists investigated, it was determined that the town was built on the deposits of an even larger prehistoric slide. So the area was prone to mass wasting events. And here you see some of that slide. The cemetery, which was built on the highest part of the town, was not covered. It stood high among that mass wasting event. We've mentioned several different types of mass wasting events so far. I've noted a rock fall and some landslides and debris sledges. We have different types of mass wasting events that can be classified on the rate of movement, the type of movement, and the type of material involved. What we're going to do is look at the rate of movement first. We're going to talk about the rapid visible movement of material. These are the landslides that occur very, very rapidly, rock falls very rapidly. They're dangerous. They often result in loss of life and property because we have no clue that they're coming. They can occur very, very suddenly. On the other hand, we can have slow mass wasting movements, and these are detectable only by the effects they leave behind. If you sit in a lawn chair and look across at a slope and a slow mass wasting event is occurring, you're not going to notice it. You can sit there for a couple of days and you still won't notice it occurring. It's imperceptibly slow, but these slow mass wasting events are responsible for the movement of the greater volume of earth materials, so they have a big impact. The type of movement can be several different types depending on how the material is moved from a higher location to a lower location because of gravity. A fall is very simple. A slide can move along a rupture surface, and a flow is where the material is going to behave as a liquid. We're going to take a look at each of these. The type of material involved, we can be looking at rocks, or mud, finer sediments, or debris, just an amalgamation of all sorts of earth materials. Let's start with rock falls. In a rock fall, it's as simple as it sounds. This is rapid movement. Basically, the rocks are breaking along joints or fractures, as you might suspect. Weathering, the physical weathering and frost wedging processes are very important here in rocks breaking along joints or fractures. And this results in what is known as talus accumulation, basically broken rock piles at the bottom of a mountain. Here is a diagram showing, here's a rock fall in place. You can see those rocks falling down. We have a lot of fractures in the rock. Frost wedging, very important process because the water that seeps into those fractures, if it freezes overnight, ice takes up a larger volume, so it breaks apart those rocks. Broken rocks accumulate at the bottom as talus. This is a rock fall that occurred along Highway 70 in California, July 25th, 2003. I don't think these people anticipated the rocks in their living room when they returned to their home, but a rock fall is responsible there. And here we see some talus cones in the Canadian Rockies, rocks accumulating at the base of the mountains. Slides, on the other hand, we're moving along a rupture surface. A fall, we have a rock falling through the air. It's not riding along a surface. A slide, on the other hand, involves a rupture surface. We'll look at that in just a couple of slides. Slides can vary from slow to rapid movement, and the material may be a variety of things. We may be looking at soil, rock, or perhaps a combination. Some types, for example, rock or block slides, we're moving along a planar surface, a nice flat planar surface. Slumps, on the other hand, involve movement along a curved surface of rupture. So slides can be rock or block slides along a flat planar surface, or they can be slumps where we have movement along a curved surface of rupture. This is a rock slide. Notice that the plane along which that earth material is moving is flat. This is a rock slide in Laguna Beach, California. California is often affected by mass wasting, but believe it or not, there is one state which actually comes in ahead of California in mass wasting events. If you live in Oregon, congratulations, you are the state affected most by mass wasting. In this case, the rock slide in Laguna Beach resulted because of the cliff. It was undercut by wave action, and that's partially to blame here. This is a famous slide. This is the Frank Slide in Alberta. Joints parallel to the mountainside and mining contributed to this slide, which occurred in 1903. When geologists came back much later to investigate, they found that these huge rock blocks had moved quite a distance, and they probably traveled by riding on a cushion of air, as some geologists hypothesized. And this would be known as a rock avalanche, a process by which these huge blocks of rock travel farther than you would calculate, probably because they were riding on a cushion of air. Rock avalanche. Here's a landslide at San Juan Capistrano. The developers were grading the slope at the hill's base, and didn't work out. Now, a slump is different from a slide. We're still moving material down along a along a rupture surface, but in the case of a slump, note that the rupture surface, the material is moving away along a curved, let me go back, along a curved rupture surface, outlined in red. Slumps are curved, and rock slides or block slides are a flat, planar rupture surface. This is a famous slump, 1958, in the Pacific Palisades in California. The red circles down below in the lower, almost left-hand corner, are actually encircling massive earth-moving equipment. This is a slump in Louisiana along a bayou. A leaky sewer pipe was implicated in this slump. We've talked about flows, and we've talked about slides moving along a surface of rupture. If the material behaves as a viscous fluid, we get a flow. A flow can be very, very fast or very, very slow. For example, we can have mud flows that have lots of water, up to 30% water, and move very, very rapidly. A debris flow has coarser debris, such as trees, and it moves a little bit slower. Earth flows, we're looking at more blocky earth material moving downslope, flowing downslope. These tend to be slow. Quick clays, a flow in which the clay will spontaneously liquefy and flow like water. And we'll look at these as well. Here is a mud flow, Estes Park, Colorado. Very rapid movement of material downslope. It behaves as a thick liquid. Here is a debris flow. This is Storm King Mountain in Colorado, and the precedent events were a 1994 fire, a very bad fire, wildfire that got out of control. And the rains following the fire were responsible for this debris flow. Earth flows move slower. Quick clays. This occurred in Nicollet, Quebec, Canada. There's a house that I've circled for you that traveled several hundred feet but suffered little damage. The 1964 Alaskan earthquake turned the Bootlegger Cove clay into a quick clay, and numerous slides occurred. The clay flows as a liquid. The rubble in the background, right there, was once an apartment building. Solifluction. Solifluction is a slow mudslide. We have a liquefied mass of material, and solifluction is common in areas of permafrost. The continuous permafrost areas in this diagram are shown in lavender, while the discontinuous zone is represented in blue. The solifluction flow on the right was photographed near Susquehanna Creek, I probably pronounced that incorrectly, in Alaska. I used to tell my geology students in Louisiana that this is what happens when a Cajun builds a hunting cabin in Alaska. In Louisiana, people commonly build directly on slabs, but that won't work in areas of permafrost. Which areas in a cabin or house would generate more heat? The heat from the kitchen, for example, would melt the underlying permafrost and result in solifluction. Okay, creep. Creep is imperceptibly slow. It's the most widespread and significant mass wasting event, though, in terms of monetary damage. It's caused by heating and cooling, wetting and drying. Changes slowly accumulate over time. You can't see it, you can't watch it occur, so how do you know an area has been affected by creep? It leaves lots of signs. Here's some great examples. Tilted headstones, for example. How many of you have been to Tombstone, Arizona? If you have, you would notice that many of the tombstones are tilted, and you might suspect that the tilted headstones resulted when people burying the dead weren't really careful about who they were burying, but that's probably not the case. It's more likely that the ground is slowly moving downhill, taking that headstone with it. Note the curved rock layers in the lower left diagram, and again, this is occurring very, very slowly, so we are bending rock layers rather than breaking them. Note the bend in the tree trunk. Okay, the tree wants to grow straight up, photosynthesize. There is a retaining wall at the bottom as well that has been affected. Here are those curved rock layers up close and personal. The tree trunk, as the slope moves downhill, the tree adjusts its growth. And there's a retaining wall that's not doing such a great job of retaining. Now, we've outlined different types of mass wasting events: falls, slides, slumps, flows, creep. But in nature, we often have very complex events. Many mass wasting movements involve more than one type of movement and more than one type of material. For example, in this diagram, we see a slump that has then moved into an earth flow. So mass wasting is responsible for a lot of material moving downslope because of gravity. We can have very quick events, rock falls, landslides, mud flows, responsible for a lot of property damage and killing individuals. Creep, again, is responsible for the most monetary damage, and this can result simply because we have a slow downhill movement. Broken gas lines, foundations can cause a lot of damage. What can we do to control mass wasting events? Well, we can try to predict when they will occur. There are slope stability maps made by geologists to alert individuals of where mass wasting is more likely. Not all geologists interpret the data the same way, however. Here's a map that shows some slope stability. And here is a photograph where different geologists predicted different landslide-prone limits. The yellow one really increases the area of that red outline, and I don't know if you can pick it out, but there is a blue line that actually goes off of this photograph that one geologist suspected was prone to landslides as well. So geologists will disagree often on what area is more susceptible to mass wasting. But a classic example of individuals who ignored geologists' warnings. The Vajont Dam, it was in the Dolomite section of the Italian Alps. It was proposed as a reservoir in spite of the geology. It was completed in 1963. It was approaching 300 meters tall, so it was going to be the tallest dam in Europe. But let's take a look at the cross section. Okay, and you can see that we have some layers that are tilting in the same direction as the slope. Uh-oh, that's not good. We know that the geology will affect mass wasting events. So during the third filling of the reservoir, they had problems all during the construction of this thing, and they noted that there were problems, and then they'd back off filling the reservoir and try to address the problem and fill it again. But during the third filling of the reservoir, the shale layers slid over the Jurassic Dogger Formation. You can kind of see the little outlined areas where that material moved. And here's a picture of the dam site 28 years after the 1963 landslide. I have another one as well. There's the scarp. Unfortunately, the sliding mass caused a huge wave, because remember, they were filling the reservoir. There was water in it. So this sliding mass caused the water to flood a village on the opposite side of where the material ruptured. And then that huge wave proceeded over the dam face and went down the valley. About 2,500 people lost their lives in this event. And as you see now, it is not filled. It's a horrible place to put a dam. The geology and the rocks are completely wrong for a dam. Other than predicting, what can we do? We can perhaps protect an area, use wire mesh to catch rocks. Well, in some areas it might work, but you can see that this sort of road cut has been covered with wire mesh. Of course, after it catches a couple of rocks, this is what it might look like toward the bottom. It probably saves cars and some lives, but it is definitely not going to do a heck of a lot of good if you have a huge mass wasting event such as a rock fall. There are avalanche protection structures. This is in the Canadian Rockies. The idea here is that avalanches, a snowfall, will move rapidly across the dam and spare the road. We can try to prevent mass wasting events as well, and one of the most effective is to de-water a slope, get the excess water out, because mass wasting events are often triggered by rain events. Here you see a diagram showing how there are pipes, and notice there are holes in the tops of the pipes to take water that's infiltrating, percolating down through the rock layers and transport that water out of the slope. Okay, here we have a terraced area. It's channeling the water away. That's a very steep slope, and you can just about imagine what would happen if it's laden with a lot of water. In addition to dewatering a slope, you can also try to reduce a slope. Here we have a steep slope before, and what the engineers have done is to take part of the material up at the top and make a more gradual slope down at the bottom. I'm not sure how they added that material without killing that tree, but that's another story. Terracing, benching can also work as well. Break up the slope. Retaining walls may prevent some mass wasting events. Here you see some attempts to prevent. There's a nice retaining wall right there. Notice there's a drain pipe moving from the slope to the roadway, so it's actually dewatering that area. It's not trapping the water behind. Vegetation planted on the slope does a great job of holding together some materials. That's why we had kudzu brought to this country to stabilize some construction sites. We weren't quite aware of how rapidly it spreads, so we have an invasive kudzu problem in many areas now. But vegetation can help to stabilize a slope. And there is a great protective retaining wall in place. But as you can see, when you compare this to wire mesh, for example, this is expensive. So it's a funding problem, and which areas are more susceptible, and which areas can come up and allocate the funding for these types of retaining walls. Rock bolts are used in certain areas, in mountainous areas, to anchor some rock bodies to a more stable bedrock. And they are just like they sound. They are bolts moving through the upper surfaces, anchoring down to stable bedrock. And here you see a wire mesh, and those big silver things within the wire mesh are rock bolts. I've also seen rock bolts extending about 3 feet away from the stable rock, and of course the rocks they were trying to hold in place have long since mass wasted away, so they don't always work. But predict and prevention are key here, and of course we need to protect areas that are prone to mass wasting events. Well, that will conclude the presentation today on mass wasting. We did that very, very quickly. That was a rapid mass wasting event. So if you need more detail, consult your textbooks and your assigned readings, or post your questions on the discussion board. Feel free to ask your instructor for clarification. Thank you so much for joining me today, and have a great day.